Okay, after a short break, we are coming back to explain about the fermentation reactions, how to use stoichiometric uh, formula in the calculation to perform the fermentation reactions. So, about the fermentation reactions, they are also coming from the anaerobic microorganisms, but sometimes they're using organic substance as their electron donor and also their carbon sources. But however, they cannot completely oxidize those uh, organic substrates. So generally, they will convert those organics to another organics, uh, like the ethanol or like the carbon dioxide, and also like some kind of the fatty acids things. So they cannot completely oxidize those organic carbons to like completely convert them into CO2, but they will have like residues, organics products left. So under these conditions, we will have like sometimes if we are just doing a very simple fermentation, for examples, here when they're using like uh, glucose as their carbon sources or electron donor, so we can have the electron donor have reactions starting from the glucose and to convert them to CO2. And the the other way is their electron acceptor reactions is coming from generate like the methanol as the final end products. So they will use these chemical reactions to generate ethanol as their byproducts. So use this as the electron acceptor uh, have reactions. So with the mix them these two together, you will get like starting from the substrate glucose and convert them into the ethanol as byproduct. Okay, so by using this, if we assumed the Fs in this equation is 0.22, and so the Fe would be like 1 minus 0.22 equals 0.78. Okay, so we also use the cell synthesis formula starting from the ammonia as the nitrogen sources. This one, so we'll get like the Fe times Ra and the Fs times Rc plus these two and the minus the Rd. Okay, so here we can get like for simple fermentation stoichiometry, we means we have only one organic carbon substance as their substrate, and we only generate one end products. So this is called simple fermentation. And so combine this here, they probably would be the overall reaction would be like you use 0.04 molar of the glucose and to convert into 0.01 molar of the C5H7O2N, the bacterial cell, and also generate 0.065 molar of the ethanol, and also the 0.0676 molar of the CO2. So the this equation indicates that, okay, so for every equivalent, which means every electron, okay, of the glucose fermented, so you will generate like 0.065 molar of ethanol converted from the glucose, and also you will need like 0.011 molar of ammonia to produce the 0.11 uh, more molar of the microbial cells. Also, so this is we call the simple fermentation. This is just coming from one electron donor to one electron acceptor. However, generally, most of the fermentation reactions not just including one electron donor. Sometimes they were including one more electron donor, such as they use multiple fatty acids as their electron donor. And sometimes they are also generate more than one electron acceptor byproducts. So during this moment, we will have to consider if we got multiple electron donor or multiple electron receptors within uh, the fermentation reactions. So that, as we call here, the mixed fermentation. Okay. So about the mixed fermentation, generally they are coming from the incomplete fermentation. So they will generate like sometimes the fatty acid as their end products, including like acetate, propionate, and butyrate. Okay, so these three like fatty acids coming from their uh, organic substrates. So in order to calculate the stoichiometry uh, reactions by using multiple electron receptor or multiple electron donor, we have to also like calculate their electron equivalent weight and just giving them like a portion of the ratio. So including in order to calculate the ratios, we will understanding that the overall reactions here, we still need to like balancing them and finally summation them into one electron reaction. So for this moment, we have to divide these one electrons to maybe uh, the first electron receptor, or part to the second electron receptor electric. And also this will need to sum as plus is sorry, this all plus together equals to like one electron reactions. So by doing this, we can directly see the example following here. Like if we got two byproducts, okay, from the citrate fermentation, so which means we will have two electron receptor reactions. So if one bacteria that converts 1 molar of citrate into 1 molar formate and 2 molar acetate. So here we will understanding that, okay, so you got the citrate as your substrates, and you will convert them into formate and plus acetate. So you got the two byproducts. So these two byproducts will be identified as electron acceptor reactions. Okay, so if we move back to the table 5.4, and we can looking for the formate and the acetate reactions. So the acetate will be like the 0.1 reaction, and the formate will be like 0.8 reactions. Okay, so by doing this, if we move a little bit here, so by doing this, okay, the acetate reactions will be like okay, 1s CO2 plus NaCl, which is CO3 minus, plus nitrogen plus, okay, electron, and get, okay, this is its half reactions plus, so which means if you want to convert 1 molar of acetate, so here you times 8, so here the electron also times 8, so you got 8 electron okay, for 1 molar, okay, acetate conversion. Okay, and for the formate, you will have like 1.5 bicarbonate plus proton plus electron, and to get like 1.5 formate and 1.5 H2O. So also, if you want to convert 1 molar of formate, you will have to times 2. So here also times 2, you got 2 electrons for 1 molar formate. Okay, so how to calculate how to calculate this? Oh, sorry. So here we'll see we need to understanding the summation of the how much amount the electrons involved in the reactions. So if we going back to the example here, so they are converting 1 citrate into 1 molar of formate and 2 molar of acetate. So we will have the total electrons involved in the reactions will be like here 1 molar of electron for 1 molar of a formate. So that's 2 electron and plus 2 molar. So here we have 2 times 2 molar acetate. That is 16 electrons. So here's equals to 18 electrons involved in the reaction. And the above here will be like every we call every substance. So for example, if you are looking for the formate, here will be 2, or if you are looking for the acetate, here will be like 16 things. Okay, so by doing this, we are calculating here. So for the electron portion for formate, that would be 2 times 16, and here will be 2. So this is about 0.111. Okay, so for the acetate, there will be like 2 plus 16 here, and here is a 16. So that is 0.889. Okay, so the assumption here still, okay, together still equals to 1 electron. Okay, reaction. So by doing this, we can get the overall electron acceptor reactions by calculating. So we calculate the E formate times the R formate, and also the E acetate times the R acetate. Okay, so then we move these two, we summation these two reactions together, so we still got the 1 electron, the final 1 electron acceptor over reaction here, and then we can use this reaction to calculate the following. Like you can combine them to any electron donor substrates, and also using the cell synthesis to get the final overall reaction. Okay, so this is for if you've got multiple electron acceptor, and by using the same concept, you can also calculate the fermentation with the mixed donor and also the mixed products. So for example here, if you got multiple organics as their common sources and electron donor sources, so here they are getting like a lactate and glucose as their two mixed donor. So by using the formula from table 5.5 and 5.4, you will have like also here how much amount of electrons you involved in 1 molar of the substrates converted into their byproducts. So we can calculate the summation and calculate the portion numbers, but the summation, finally summation for the electron still got 1 electron. Okay, so for the same concept, if you are converting them into multiple byproducts, for example, here is the methane, acetate, and the propionate. You can also calculate how much amount of the electron they involve per molar of the substrate, and also got the electron portion. So finally, you still got one uh, electron involved in. Okay, so for the next page, you can just combine those things together. So here you got three electron receptors. Got the final electron receptor reaction, and also you will have like a two electron donor, and you got the final electron donor reactions. And so finally, you can still use uh, like combining them with the cell synthesis equation, the RC, and to calculate the overall reaction. Okay, so we just move the example here. Okay, for our next part, we are moving to the energetics of bacterial growth. So from previous discussion, we talking about the stoichiometry uh, reactions combination to the overall reactions from electron donor to electron receptor, and also to the how much amount of the cell synthesis. So we know the mass balancing about the chemical reactions, and these parts we get into more detail about how much free energy they can harvest from the overall reactions. So by understanding here, we can know like uh, we're using the oxidation reduction reactions in order to obtain energy. So here's energy we call the free energy, and the free energy will separate them into like the part of the energy using for cell growth and part of the energy using for cell maintenance. So as we just mentioned previously. Okay, so how much amount of the electron will release per electron equivalent? So we have those chemical reactions listed in table 5.4 and 5.5, and they also including the free energy for every half reactions. So let's just very quickly move back to our table, every table, any table here. Okay, so for example here we can have like the electron uh, donor reaction, half reaction here, and we will see here is the free energy under a standard condition, as we will mention what is the standard conditions later. So basically they are per electron converted, how much amount of the energy, free energy, as in kilojoule you will get. So here, like for acetate, converting one electron reactions, you will get like 27.4 kilojoule. Okay, so let's move back to here. Okay, so we need to calculate Okay. How much amount of energy released per electron, but that's just half reaction. So finally, we need to merge them into like one complete reactions from oxidation to reduction. Okay, so for the following, we move to the next page here. Okay, so about the free energy of the uh, of the half reactions. If you would like to learn how to calculate the free energy, there is appendix. They can use like every compounds have their like free energy state. So basically, you can use the molar ratio of the uh, organic compounds and also the chemical compounds to convert them into the overall reaction of free energy. So we don't explain this too much because we didn't provide the appendix to you guys. But most of the free energies you can get from table 5.4 and table 5.5. And so we just move a little forward to the next page here. Okay. For most of the electron acceptor and the electron donor reactions we list in table 5.4 and table 5.5, we got their free energies in the reaction, and so we can use them to calculate the overall free energy uh, by converting two reactions together. So, for example, here if we use ethanol as our electron acceptor, and by doing the aerobic oxidation, so which means our electron acceptor will be like oxygen. So we can look into their half reactions listed in table 5.4 and 5.5. So here we get for the oxygen's half reactions, we got I14 reactions here. So their free energy is listed in the table is minus 78.72. And for the ethanol oxidation reactions, we got their electron donor half reactions from O7. So which means they got the half reactions free energy is minus 31.118. So if we combine these two reactions together, okay, so we will get like minus 109.9 of the free energy by converting one electrons. Okay, and so the overall reaction will be the ethanol plus oxygen converting to CO2 and H2O. Okay, so the standard free energy here with this here, we will uh, write in as delta GR, and this is the standard condition. Okay, that is specifically under the condition that is for the gas is 180 and partial pressure, and for the uh, liquid condition will be like the pH is fixed at 7. So because we need to consider the proton concentration here, so which means under the standard conditions we consider that this is under the pH at 7 condition. And the other thing would be, okay, most of the uh, reductant or the byproduct concentration will be 1 molar. Okay, will be 1 molar. So this is mean the standard condition. As we go the reductant, no, reactant, okay, sorry. Reactant concentration is 1 molar and the pH equals to 7 at a 7 condition, and also the if we got any gas uh, reactants that is under 1, okay, 1 atm partial pressure. So this 3 equals to the standard conditions. Okay, so this is the way we think about the free energy. So if we got a different combination of the electron donor and the electron acceptor, we can move to the next page to see these figures. Okay, so in these figures, we can understanding the correlation and also how much amount of free energy they can generate by combining different electron donor and the electron acceptor. So for example, as we just saw the ethanol here, and by using the oxygen as their electron acceptor, so here is the electron donor. So this list is electron donor as y-axis, and the electron acceptor will be like the oxygen, nitrate, sulfate, and the CO2. And the x-axis will be like how much amount of free energy they can get under the standard condition. So how do we see this figure? How do we understanding this figure? So for example, we just saw the ethanol here. So we crossing the line together to get the oxygen as the electron acceptor here. So how much amount of uh, free energy we can get from the standard under the standard condition will be like here as we just say, okay, 109 kilojoule per electron equivalent. Okay, so from these figures we can understanding that by using the electron acceptor, by using oxygen as the electron acceptor and also the nitrate as electron acceptor, they are very similar. They will get a very similar amount of free energy after their reactions. For example, if you're using ethanol here, so you can see they're just a little bit different, but they still got lots of the free energy. However, if you are using like a sulfate as their electron donor under anaerobic condition. So sometimes you will get a very few amount of electron, free little amount of the free energy, and sometimes they cannot like maintaining uh, their biomass generation. So sometimes most of the energy they can get to by use those energy they can get is using for like a cell maintenance. Okay, so by this figure you can considering which electron receptor will be more valuable to generate more free energy. Okay. So we move back to here. Okay. So for the previous discuss, we talking about the standard condition. But however, if we are looking in the real world, the reductant and product concentration is not always 1 molar concentration. So the actual reaction and product concentration would affecting the true reactions free energy. So we move to the next page here. So this equation is using for calculate the real. Here is the real free energy. Here is the standard condition. Okay. And so plus the RT, the R represent the uh, universal gas constants, and the T means the absolute temperatures. And here is the equation that is using for uh, here is the part of the calculation related to the chemical reactions. So we can see one example here. Okay, if you got the reactions here as we just saw previously by using the ethanol and oxygens to convert them into CO2 and H2O, and you got the delta GR under standard conditions is minus 109. Then how about the real free energy calculation? So here we will using the overall reactions. Here we see for the reductants their molar ratio, okay, is 1/12. So for oxygen their molar ratio is 1/4, and for the products CO2 their molar ratio is 1/60. For the H2O is 1/4. Okay, so we will generate the calculation by doing the here is the products and here will be the reactant. Okay, so if we want to calculate the real concentration here, we have to like put their concentration here and have times their molar ratio in the power. So basically you can just detailedly calculate the every concentration. And so for example here, if we got okay The CO2, okay, the ethanol real concentration in aqueous solution is 0.002 molar. It's not 1 molar under standard condition. Okay, so if the oxygen partial pressure is 0.121 atm as in a gas, okay, 21% in a gas, and the CO2 concentration in the air is 0.0004 atm, and the temperature is 20. So we can, using those real concentration, then move them into the uh, like modification calculation. So this part is for the ethanol, and oxygen will be like 0.21 here for the oxygen, and the CO2, sorry, CO2 here is 0.004. Okay, so the real delta GR here will be the standard delta GR 0, and this is the R, the universal gas condition, gas constant, and this is the absolute temperature and times the natural log, and here is the real concentration calculation. So by doing this, just a a little bit difference from the delta GR. Okay, so there will be the minus 110. So just a little bit different, but this is for the real delta free energy you can get. Okay. So by doing this, after we understanding every reactions energetics and calculating their real free energy, we can use the free energy, how much amount of the free energy we can get to theoretically calculate the microbial yield coefficient. Okay, so the first thing we are going to understanding the microbial yield is the energy reactions create high energy carriers such as ATP. Okay, and the energy carriers is spending to drive cell synthesis and also the cell energy maintenance. Okay, so they got two steps to using those energy they harvested from the oxidation to reduction chemical reaction. Okay, so which means if we can combine in the concept we previously used for the true yield and also for the portion of the electron using for cell synthesis, we can use the following equation trying to understanding how much amount of the free energy they are that's using for cell synthesis. So by understanding the cell synthesis process, the first thing is if we come understanding assuming the ammonia is a nitrogen sources first, and generally under the carbon central metabolism, the pyruvate will be okay. Pyruvate will be the like the most important carbon intermediate to all the carbon central pathway. Okay, so we consider it as a representative intermediate to synthesize any like a cell portion and also the macromolecular things together. So this like kind of the central carbon intermediates we are thinking about. Okay, so to synthesize pyruvate, we need like their precursor as acetyl CoA. Okay, so the acetyl CoA, the reduction free energy is 30.9 kilojoule per electron. Okay, so we think this compound is much relevant to the pyruvate synthesis, and because it is its precursor. Okay, so by understanding this, we can use this as a representative uh, free energy that consuming for cell synthesis here, and so the delta GP will be like how much amount of the free energy uh, they took to using for like the biomass synthesis, and so the delta GC. Okay, here we also taking from the table 5.4 to understanding how which electron donor they are using here. So which means they using electron donor part of the electron donor free energy and converting them to acetyl CoA. This portion is using for the cell synthesis. Okay, so for example here, if we use electron donor, uh, acetate is our electron donor. So here is acetate. So by looking at their free energy, it's about 27.4 kilojoule. Okay, so which means your delta GP would be like 30.9 minus 27.4. Okay, and if they are using acetate as the electron donor, which means they are heterotrophic bacteria. Okay, so if there are like autotrophic reactions, so they will use like inorganic carbons as their carbon sources, and in natural uh, sometimes electron donor will be like the inorganic carbon. And for photosynthesis, they will use like the oxygen uh, converted to water reactions as their electron acceptor reactions. So during that moment, you will use the water oxygen reactions from table 5.3 and their free energy to calculate the delta GP. So your delta GP for the autotrophic, especially for photosynthesis, will be like 30.9 uh, minus the minus 78 times 0.72. Okay, so that would be for the delta GP for photosynthesis autotrophic bacteria. Okay, so our next part will be understanding the energy required to convert the acetate to the cellular carbon. So previously they are converting to the intermediate, and here we are considering if they are converting to the cellular carbon, how much free energy they need. Okay, so the delta GPC is basically like you will get 3.33 kilojoule per grain cell. That's how much amount of energy you require. This is basically according to the literature from McCarty since 1971. Okay, so which means you need to understanding how much grain of the cells you will get synthesis here. Okay, so per grain cell synthesis, we know that, okay, per electron equivalent of a cell synthesis, we got 113 grain for 20 electron. So which means per equivalent electrons we will get like 5.65 grain cell. So the 5.65 grain cells times 3.33 kilojoules, which means if we are considering per electrons converting to the cell carbons, our delta GPC, the unit for the delta GPC will be kilojoule per electron transfer. So which means that would be like 5.65 grain per electron times 3.33, okay, kilojoules per grain cell. So here we will get like 18.8 kilojoules per electron equivalent as our delta GPC. Okay, so right now we got one portion is the electron donor converting to the acetyl-CoA as the major intermediate, and also another part would be like the electron donor to synthesize how much amount of the cellular carbon. Okay, so if we want to understanding the real and summation of free energy that is using for cell synthesis, we considering the delta GP and the delta GPC, and then dividing them into and divided them by the electron transfer efficiency epsilon. So the epsilon here, they also studying uh, how much amount of the epsilon we need to use to to different microorganisms. So for example, we can firstly move to the next page here. Okay. So here is talking about the energy transfer efficiency. Okay. So the energy transfer efficiency, which means you will get energy losses, converting them to heat. So the energy transfer efficiency they understanding for like a heterotrophic microorganisms or for chemotrophic reactions. Sometimes they will find out that 55% to 70% is typically for the is typically the energy transfer efficiency for most anaerobic or chemoautotrophic reactions. And so they will pick up the epsilon value of 0.6 using for this kind of the estimation. And also for the aerobic heterotrophic organics, sometimes they found the average epsilon here would be like 0.38. Okay, so those numbers is empirical and coming from the literatures. So sometimes we will use this numbers as our estimation for the epsilon. Okay, so here you will get like sometimes for 0.6 for anaerobic or chemoautotrophic bacteria, and the 0.3A for aerobic. But you also can doing like a summation of using different numbers to calculate the delta GS. Okay, so our delta GP will be divided uh, by the energy transfer efficiency epsilon, and here is the power of n, which means you got uh, the actual free energy from this conversion over the free energy is lost. So which means if the delta GP you calculate here is negative, okay, if your delta GP after your calculation, so delta GP will be 30.9 minus the delta GC 0, and this GC 0 here is coming from the electron donor substrates. So for example, if you got minus, as we just have the previous example as acetate here, okay, so here you got is 3.5, okay, kilojoules per electron, so which means it is positive, okay. So if you got positive, okay, which means, okay, the energy is lost. Energy is required to converting the acetate to acetyl CoA. Okay, so by doing this, we have to get the n numbers as +1. Okay, by another examples, if you are using the glucose as your uh, electron donor or carbon sources, your delta GP will be like 30.9 minus the delta GC, and which means 30.9 minus the glucose equation is all 9 equations in the table 5.4, so which here is the 40.95. So this is negative, okay, about -10. So if they are negative, which means they will get free energy from this conversion to acetyl CoA. So during this moment, your n was taken to the -1. Okay, so this, okay, so this equation represents the free energies using for the biomass synthesis or the cell synthesis. Okay, so after this, we will need to estimate, okay, so how much amount of the free energy is using for the cell synthesis. So we assume here, okay, if we define the amount of energy as A equivalent of electron donor, so which means the A portion is going to as the electron as the energy released from the donor oxidation. So from the delta GS, we know how much amount of the energy we need to synthesize uh, like the biomass. So right now we can estimate how much electron donors will be needed to supply the energy that's using for the uh, biosynthesis, biomass synthesis. Okay, so here we assumed A as the equivalent portion that is using using for the biomass synthesis free energy, the portion ratio. And so if we're using A, the ratio times the delta GR, and the delta GR means the free energy that is released per electron equivalent from the electron donor. So this is the overall reactions we get from the energy. So this portion times the A ratio, which means they are going to synthesize the delta GS. Okay, but as we will see here, okay, so by considering this like the energy balancing, we still need to uh, times the energy transfer efficiency, because you are not converting 100% of the energy to the cell synthesis. So which means your A is the ratio times the epsilon, okay, times the delta GR, the overall free energy you can get from the oxidation reduction reaction will be like equals to your delta GS. And because they are like one is the providing, another one is harvesting, so you will get like a minus, okay, symbol here. So by calculating this, we put the delta GS into our equation. So the delta GS is epsilon n delta GP plus epsilon delta GPC. Okay, so we divide this, okay, to the epsilon delta GR and get the minus here. So this is the why the 5.31 the equation coming from. Okay, so which means this portion is, if you can calculate this portion, and this portion is means they are using for the cell synthesis. So by understanding how much of the how much amount of the A ratio that is used for biosynthesis, we can combine in their concept to our FA0 since. Okay, so which means this portion will be for the FS that is using for the cell synthesis, and another portion will be uh, 1 minus FS0. So this is using for the energy maintenance, cell maintenance. So by calculating those free energies, we can get the FS0 and also FE0, the ratio, and so we can like uh, modify and correct the real overall reactions. Okay, so let's move to the next page here. So we can have like an example 5.9 to understanding more about how we can get FS0. And also if we have FS0, we also can get the true yield. So how to get in those numbers from if we considering their free energies. Okay, so here the examples. They are using acetate as their electron donor in the carbon sources, and for oxidation, which means they are anaerobic with oxygen. Okay, so here they assume like pH is at 7. Okay, and they are all unit activity, which means they are under standard conditions. Okay, so ammonia is using available for cell synthesis. Okay, so we understanding the reaction is heterotrophic. Okay, so acetate is from the O-1 reactions. Their delta G under standard condition is 27.4 kilojoule, okay, per electron equivalent. Okay, so first, since its delta GP will be like 30.9 minus 27.4, so this is plus this is positive 3.5 kilojoules per electron. So which means they require energy to convert the acetate to the acetyl CoA. So which means here your N will be equals to, okay, +1. Okay, and another is your overall reaction free energy. So overall reaction free energies, we know this is our donor, our acceptor is oxygen. So the oxygen's free energy is minus 78.72. So your delta GR will be the acceptor minus the delta G donor. So which means they are minus 78.72 minus 27.4. So which means they are minus 106. Okay, so this is your delta GR. Okay, so your delta GPC is still 18.8, which means they are using, okay, um, they are using ammonia to synthesize the biomass, so they're still 113 and per 20 equivalent electron equivalent. Okay, so that's your delta GPC. Okay, so by calculating those things together, you can get the A number here. So the A number, sorry, the A number will be here is the delta GP, and here is the delta GPC. So get the epsilon +1, and here is the epsilon. So divided by the delta GR times the epsilon. Okay, so now we can choose different number for the epsilon to see what's the changes for the fs0. So the fs0, okay, is coming by calculating if we got the A number. Okay, so there are assuming the epsilon from 0.3 to 0.7, so which means your energy transfer efficiency is quite lower at 0.3, is quite higher at 0.7, so which means you can get, okay, basically they are very similar to, okay, the fs0. So for the first epsilon assumptions, if they are equal to 0.3, so we can put the 0.3 into the equation here we list. So the first part here is 3.5 divided by 0.3, which is 11.6, and here is 18.8 divided by 0.3, and that is 62.6, and here part is 31.8. So which means your A is equal to plus and divided by 31.8. Okay, that's minus. Here is minus. So your A will approximately equal to about 2.33. So if you put 2.33 into the equation to calculate fs0, so your fs0 will be like 1 times, sorry, 2.33, so that would be equal to like 0.3. Okay, so your fs0 will be around 0.3, and by the similar calculation, you can calculate if the epsilon is equal to 0.5 or 0.7, and you will get the different fs0. Okay, so if you have those fs0 numbers, you will definitely understand in how to get the fe0, which means 1 minus fs0. Okay, so if you have like assumption with epsilon equals to 0.5, your fs0 is 0.54, your fe0 will be 0.46. So which means by doing the chemical reactions, we still found the reactions O-1 that is used in acetate as electron donor, and we're using the I-14 that's using oxygen as electron acceptor, and we also will have, okay, our carbon, our bacterial synthesis from ammonia. Okay, so by calculating this, you will get, okay, like the overall reaction. This is your electron donor reaction. So what we will say is Fe0 times the electron acceptor plus the Fs0 times the Rc minus the electron donor reactions. So this is our overall reaction. Okay, so this minus reaction electron donor is here, and you got the Fe0 times your Ra here. So this is 0.46, okay, times the I-14 reactions, and you will also get the Fs0 times the Rc reactions. So your overall reactions will be like here. So you will consume 0.125 molar of acetate, and also require to supply 0.115 molar of oxygens, and also 0.027 ammonia molar of ammonia to synthesis 0.027 molar of the biomass and converting to release 0.017 CO2 and also the bicarbonate. Okay, so by these numbers you can calculate the yield, how much amount of the, like for the acetate, or you can convert in the acetate to COD. So you will get like how much amount of the molar acetate is converting to how much gram of the cell, or how much amount of the COD is converting how much amount of the cell. So this is our yield number. So basically, by understanding the stoichiometry and also the energetics, we can get the real uh, estimation about the biomass yield, and this is very useful for the following microbial kinetics modeling. Okay, so here is another example talking about the effect of electron receptors, and I will recommend you guys to like following this equation by yourselves to understanding if we using different electron receptors. For example, here is oxygens we just used before, and if you are changing to nitrate, sometimes they is the condition for denitrification. So how much amount of the delta GPC and delta GP you will get to calculate those A numbers and also for the FS0. And as we saw for the sulfate and the CO2, the different electron receptors, you can see here there are A numbers getting larger and larger, and so their FS0 getting smaller and smaller. So which means most of the energy is using for cell maintenance instead instead of the biomass synthesis. Okay,